This talk is called An Autonomous Terrain Coverage and Marking System for Humanitarian Landmine Clearance. Now, clearing of landmines is a topic that's ripe for robotics and automation, but as you might see from the images here, there's been relatively little change in the last 100 years. It operates in quite a similar way. One of the reasons why robotics hasn't made too many inroads possibly is that it's not just a navigation challenge for robotics, it's a human awareness challenge. Now, the problem is that you need to know exactly where the area has been covered, and it needs to be guaranteed that you have actually covered those areas. The UN has some regulations that you need to mark the area that's been cleared in a landmine clearance task. And the most normal technique that they use is the use of red and white markings. And at the moment, people use things like sticks and stones. And but what we're suggesting is that we make use of an autonomous vehicle for demining, and the vehicle will be laying down paint, white paint on the left side and red paint on the right-hand side. Now, this is the idea, is that we use this autonomous vehicle for doing the landmine clearance, but we're looking in this paper at the worst case scenario, which is a scenario where there's no GPS, no ground stations, and no LiDAR or SLAM. So what we want to do is to actually make use of the lines that we paint for the navigation itself. So the idea is that we have an existing vehicle, in this case a John Deere Gator, and we attach a system on the front which will use magnetic coils for detecting the landmine and eventually deactivating the landmine. But that's not part of this talk. The talk is about how we navigate the fields accurately. This is the setup from above that we've used for the vehicle. We've automated an existing John Deere Gator, and we put in an automation kit in order to control the servos, which will control the steering and the acceleration and deceleration of the vehicle. On top of that, we have an i7 processor that's used on board for the autonomous navigation, and we have a painting system which is able to spray a large amount of paint on either side. And the setup is such that there is a spray painter that sprays white paint on the left-hand side and red paint on the right-hand side. And this is what we're doing is a form of visual servoing effectively, where we use the cameras set up on the vehicle in order to navigate using the lines that we've painted. All right, so this is what it looks like on the real vehicle in action. And the first task of doing this visual servoing is the actual identification of the line parts. This is made difficult in real world situations, in real minefields, by the variation in light levels. In particular, we found that there's a very large variation in the blue component. So the metric that we've used, we look at every pixel in every video frame and we convert it to an intensity. And the metric that we've used is to ignore the blue component entirely. And we also divide by the amount, the brightness of the pixels, so that it becomes invariant to brightness as well. Once we have the intensity, an intensity measure per pixel that's supposed to represent a line, the line on the ground, which is red in this case, we then apply a difference of Gaussians to convert that thick line into more of a peak, so a line which has a strong peak to it. And once it has a strong peak, then we can use the Hoff transform to convert that into accurate estimation of the line equation. Now, from results that we've tested using 8 minutes of footage in realistic settings, we found that there was roughly 1.5 seconds where it didn't work too well, and that was on a white line. So generally, the line detection has been working excellently for us. So the idea with this paper is that the vehicle follows a cone formation where it drives forwards and then it drives backwards along the path that it's driven, and then it does what we call the dogleg maneuver, where it moves to the right, to the next lane to the right, and then drives forwards and backwards using repeating that pattern until it reaches the number of lanes that it's been requested to drive. One of the reasons for doing this is that it doesn't require a turning around maneuver at the far end. Another is that it allows us to drive right up to the end of a field. So because we're using visual servoing, as you drive, you're painting down a white line on the left and a red line on the right. And then as you reverse, you have to follow the red line on the right as you're reversing. And when you move to the next lane, you have to follow the white line on the left and the red line on the left and overpaint it with white. So the main part of the control is we use a hierarchical state machine. So that's quite simple. It just means there's the base state, which we call scan field, which is a state that's only exited once we've scanned the entire field. And within that base state, we have 5 states that operate in a cyclic fashion. So initially there's a drive straight forward state, followed by the backward line tracking, followed by a small period where we drive straight backwards, where there is no line to track, followed by the dogleg maneuver, and then the forward line tracking, and that repeats in a cyclic fashion. The control system itself is just used to control the steering of the vehicle. The velocity has a very simple controller, which is just trying to reach a desired velocity, which is 0.6 meters per second in this case, so it drives quite slowly. But the steering controller, there are 3 parts. The first part is forwards line tracking, which is a simple PD controller. And there is backwards line tracking, which is a slightly more complicated form of feedback controller. But those of you who are familiar with control systems might recognize that as we're making use of a variant of a critically damped spring model effectively for the backwards driving. And then the final part is not actually tracking real paint on the ground, but tracking a virtual curve for the dogleg maneuver. And that relies on wheel odometry in this case. So here's some examples of the results as we're overpainting the red line there with a white line. And here you can see the results in the full field. We've analyzed the results in this field and calculated that the root mean square error is 1.8 centimeters. And that's over an area of 231 square meters that we've scanned in this example. All right, okay, that's it from me. Thank you very much.
If there are any questions, no questions on Slack yet. So I have a question, something I actually know the answer, but you could mention some of that to people who are listening. What do you think are the greatest challenges in the next steps when we move on to more complicated fields? Like as we saw in that example, was a very flat field. So I know we had some issues when we were on slope fields. So what are your thoughts regarding that? If you can comment a bit on that.
Yeah, that's right. It's quite a steep curve. It's one thing having this work on a flat field, and there's an awful lot of other factors that come into play when you start getting beyond just flat fields. However, on the other hand, we intend to make use of more sensors for the next steps of this project. So the current setup was trying to attack the worst case scenario where you don't have this exterioception, you don't have LiDAR guidance, you don't have localization or GPS. So we're hoping that as we're able to make use of our SLAM systems that we've got available, that'll offset some of the extra difficulty as we go from flat fields to more complex terrain. And it certainly will get a lot more complex. It's rare that minefields conveniently just land in flat fields. So there will be some, not just slopes, but very rough terrain, rugged terrain, and also obstacles and non-rectangular fields. So they're all big challenges that are ahead of us, but we hope that we've got some existing tools that can help us.
Yep. Okay. Thanks for that. And just one more comment. You mentioned wheel odometry there. Can you talk about the role of SLAM, how it could play in this sort of navigation task?
Yes. The downside of a non-flat field is obviously that it's very hard to control a vehicle and navigate through a field that's not flat. But the advantage of it is that SLAM systems work very well when there are features in the environment, and they work very poorly in a flat field. So we've got existing technology, simultaneous localization and mapping technology that's really good at mobile mapping. And so we're hoping to harness that. And we've already placed one of the units on the top of the vehicle. And we intend to make use of that for localization primarily to help us to navigate and drive, but also for obstacle detection.
Mm-hmm. So we have to wrap up soon, but just the very last question. There are a couple of questions actually regarding timelines on next phases. Can you talk about that?
Well, we don't know yet exactly what the timeline will be. It depends on external factors that are not really in our control. But in terms of what we intend to do next, the next step will be employing a SLAM localization system, and also making use of GPS while we can. And then the next step will be non-flat but smooth terrain. And after we feel that we've got confidence in that scenario, then probably it'll be non-rectangular fields. And after that, it'll be more undulating and rough terrain, which is, we believe, is the harder one.